so that I know that there is somebody who was not satisfied. Or after I felt bad that I had to choose best test or whatever, I wanted to make sure you get what you want for. So I'm sorry about that. Okay, so we go for THY 3112, which is a little bit of the applications of electricity and magnetism. So we shall get an introduction to the telecommunication engineering in one or another. But we shall make sure that we start with the basics of electricity and magnetism. And so still it comes from the two guys, electro and magnetism. And somehow, somewhere, we still have this guy being the key boss. From being stationary electrostatics, moved into stationary electric fields, causing a magnetic field around magnetic fields, and then we try to make sure that we harness the electric and the magnetic component of this electricity for this part and magnetism for this part, and then get what we call an electromagnetic wave. It is from this wave that we get communication. This same communication, if you manage to do the electronics and instrumentation, is where we shall look at the communication system, and then look at how communication is done, from transmission to the propagation and then reception. And we shall be able to have a good glimpse. And then we shall, the difference between this course and the previous course, not previous course, and the electricity and magnetism, the ingenuity of the guy called Maxwell. But before going all this far, we start from the meetings when we shall be meeting. I will not talk about Mwele because I know all of you are Mwele, but you refuse to enroll before you come, which is okay. I'm now getting used to students. Those who came a little bit later, I was going to teach myself for the day. But you have denied me a chance. So we shall be meeting today, which is Monday, from 10 to 12. The venue, I would have preferred the electronics lab. The timetable is stupid, but I don't want to argue anymore with anybody. How do you expect me to teach from physics tomorrow? And then finally, after 1 hour, I go to the physics main. And you make a timetable and you gladly put it on the notes. And you expect me to start complaining, there is this mistake. I am no longer, I'm tired. I'm tired. Nationally, locally here, so I no longer want any problems. I'm being frank. I just want to do my stuff. I'm about to get an island, slowly. If I fail to get an island, I'll build a big wall around my house. And just remain there. No, I don't need a rascal. I'll use you so that you don't come to my place. You see people who believe in juju, when you scare them with juju, they run away. is a man a kid who was playing and poured the flour around the vehicle. So the man feared to enter his own. But the kid was just playing around. To wake up in the morning, you found the vehicle and surrounded by flour. He feared to enter the vehicle, he just went to buy a taxi. Until when they discovered it was the kid who was playing around. So when you know the community you are living in, you know how to live in it. Make sure that you scare them to death. So I will manage one or another, but it's I put a notice board. On a notice board I put a notice at before 6:30. Even put clearly venue, electronics lab. You find somebody teaching and it's comfortable. And I really, because I could not even try the small room, people were repairing lights. In the morning when it is about my lecture, they are repairing lights. So I said, I'll find anywhere I find. So my one was to put another notice that now I'm in this lab. Then I think I saw a pressure and some good person. They will figure out where I am. But the truth of the matter is that I am pissed off by everything. Maybe I'm the one who has a problem on how things are working. But I'll make sure that we enjoy this course if you really cooperate. Are we going to have a problem with your friend again? Your lecturer? No, you are not in education. I'm asking this one. I have never talked about colleagues. I normally don't care what. From the time when I was teaching secondary, I never used to. I remember when I was in my first year vacation, that Susan place, there was a guy teaching physics. It was an S6 leaver, okay, vacancy. But I taught math. I pretended I didn't know physics. I only taught physics to someone guy who was a relative to a manager of the tea factory, and that guy fed us with everything. Brought maize, tea leaves, he gave me a ream of paper when I taught him physics. But to the general students, I pretended I don't know physics. But someone cannot do a PhD in heat storage and then goes down there, starts posing that he's the expert in the method, when your specialization is in a different place. And you make everybody really suffer. I suffered. You suffer. So I have already talked to his bosses. One colleague actually resigned from there. He's in biology. He was in biology. He had just come. We were together here, taught somewhere together. He went and did his PhD. He had come back. He resigned. Because they are doing nonsense. You can't teach methods and teach content at the same time. It's impossible. Let someone pour them with content, then teach them how to use that content, and life will be okay. But I want them to make a new curriculum. Like last semester, they made me teach a course to distance, which is not supposed to be run this semester, that semester. Now marks are pending, and I'm in a university. I'm sorry, you have just come now. I'm pouring my heart at you. So I don't know whether the person who was in the lab today will understand when I tell him that this is my lab, and if I taught from it, I know how to manage the equipment and keep it safe. After all, the people I teach from there are using the equipment. Nevertheless, people seem not to like this place, so I can choose we just do it here forever. Since even the space looks a little bit bigger, but we are not so many. And since this is an elective course, I will not get beyond almost 40. I don't think you go beyond 40. It's a core. It's a core. It's an elective for mathematics. So physics major you can't go beyond 40. Because we were 35, I don't think it's anyone who was major. And can you imagine one of you, okay, was a third year. The one who burnt the transformer. He came here and sat there and put wrong registration number, wrong student number. When I am filming, when I film the sitting and when I take the registration step by step, I want him, and he has a good class and he's not taking anything. I'm going to make his life a living hell. You are nice to somebody, and all I get, the only thing I've got from being nice to students is looking at me as if I'm confused. Like I don't know what I want. By being nice to students, I don't know. But I'll go read. God is there. He has already blessed me with a lot of stuff. So the next day is when? I don't have the time. 15 to 17. There, from 15, 17. So once upon a time, I used to, this is PM, but on timetable it is PM, but I still had put, even on where I put electronics lab. You know, with the hope that if the numbers are manageable, if you are not so many, and some of you are doing electronics and instrumentation, so we make the lab our place and have an environment where when we are discussing, that place is always chaotic. You are teaching, someone is busy chatting outside. Anyhow, so we shall agree. I no longer want to argue for them at all. Good enough on the notes board, they just put lab, they don't specify which lab. That's why I'm not so worried. So these are the only two, and like I said, once upon a time I used to enjoy this because there is, I think, a free lecture before, either 2 to 3 is free also, but also because I used to live here late, which behavior I have started growing again after COVID. I would teach, and the last hour, this one was 5 to 6 and 6 to 7, sometimes they used to be free. So we would go slow and then cover up everything instead of rushing through the course. And like I shouldn't be rushing to finish whatever I prepared. And we would sometimes go up to almost 7. And we cover a lot of stuff, finish early, and then be able to have time to log on. So these are the meeting times. Apart from the venues, you cannot do any amendments. These are fixed. So it's only a venue which we shall agree with time. But do you have any issues with these two doubles? It's a 4 CU. I think since the time I came, I've always taught 4 CUs. But I found them okay because I gave to give what I got. I teach my old notes, much as the syllabus is the new syllabus. The new manual, even for this course, is outrageous. At least the new manual for electronics was fairly related to the practicals we took over, but this is worse. You don't have even, it has things of temperature. I don't know, you try to look at it. But do you expect to change this continent after you have grown, or you just want to be there? Let me ask you now that you are, because now you are at the verge of getting out of this place. Do you have hopes of causing change in your continent? Or you just want to go with the wind? Where? How? Change for what?
I was asking, changing what?
Everything is okay for you? Like you look at that scene in deep in water now, in whatever I'm quarreling about, and it's okay? You feel okay? You don't have anything. You don't feel any, you don't have any urge for anything. Okay, that's interesting. You've given up. Or you are used to what you have. You adapt. You are adapted. You see, when you put a frog in a container and you start heating up, it warms up nice, it keeps there. Starts getting hot, starts wondering what is going on. By the time it wants to jump out, it is already cooked. That's how you work. It just warm you up. That's just like how rats. Anyone have ever eaten by a rat? Yeah, I've ever been eaten by cockroaches. I don't know how they eat it. But they say a rat keeps doing and then chews. So you never feel anything. When you are about to feel the pain, and then tomorrow you find your foot is having a hole. It has been chewed off some bit. The cockroaches ate me again. There's a time when I used to go home late, some long time ago, I think. And then I think they had hidden somewhere in the corner. And I felt my finger was really rugged. Eh? They had chewed me. The way they chew the remote controls, those buttons. That's how they had chewed me. So I went to rummage through my beddings and found that they had just got a corner and they were comfortable. So for me, when I'm sleeping, they come and feast on me. Then they go back and keep quiet. You don't hear nothing. So that's how you are being eaten. Like rats. Okay, so this is done. Muere is okay. Now, so we start on the. Then, unfortunately, this course has practicals, but I always find those practicals a mere wastage of time. That I will be just making you take data, draw graphs, and just not get anything about electromagnetism. But I'll, if you use Walter Lewen's videos and look at those demonstrations, and those few demonstrations I did in electricity and magnetism, and then I'll make sure the teaching is more practical, as in applications, and cite a few applications so that you can relate. Then for practicals, I'm not really into, like the way we do. So before, those who do education, how did you find the competence-based curriculum? Maybe you can convince me. It seems I'm confused. So how did you find it? Muzaffar, were you a teacher?
Yes.
So how was the competence-based curriculum?
It is like, it's not working yet in some parts of the country. Because for me,
they started it in 2020. How can you say which parts of Canada that?
especially that side of Ginger. Some schools lack resources.
Yeah, they laugh, but they're trying.
And another thing, it favors only the bright ones. The bright ones pass, they still excel. Then these people can't reason out the scenarios, they still fail.
The even scenarios?
Yes.
Okay. You seem to be very...
Okay, well, to my side, it works, but the problem is lack of equipment.
So how does it work? Because when
The few
there's...
equipment that you can have can really teach a good content.
So
Because
how working is it than the old calculator?
because you don't do anything, you keep guiding and they give you the outcomes. And
The students?
Yes.
They are bright. So they can tell you whatever you're going to teach them in
It's like
in
getting
physics.
them towards something that you need.
What is calc?
I don't know.
CAL is computer-aided learning. So how many computers were in the school you were in? How many are in there? Huh?
Yes, I'm sure.
Like how many?
Like 100.
Having internet.
Yes.
And then the total, those living without internet?
It's a very many.
Hmm?
Students are many.
The students are, yeah, I'm asking about the computers.
The computers. They're like 100.
And those which have internet, all of them have
All
internet?
of them have.
Okay. Which school is that?
Turina Church of Uganda.
Huh?
Turina Church of Uganda.
Here in Chile?
Well, okay.
Yeah, that area of 100 computers. And the school population, your class was how many?
It's around 198.
So you have a class of 198, you give them a group work, and they also, that was a stream or a class?
A stream.
And how many streams did you have?
There are 4.
So that is about 400 students.
And beyond.
Guys, I am not against daydreaming that we want to make our children practical. Tom Duncan is one of the practical textbooks, isn't it?
Yes.
All we needed was to have those apparatus in our lives. Not the write-up of how the teaching should be done, but having those practical. So that when I'm teaching students, I can go to the lab, and when I talk of an ammeter, each student is holding an ammeter. So when we are drawing that millimeter, diagram, each student is having a millimeter and is looking at the windings on a, aluminum frame and etc. Now here at the university, we had how many sets in electricity and magnetism? 4. Of different experiments, not just one experiment that you have 4 sets. And we are at Premier University, we go around boasting that we are the best, we are Harvard of Africa. And then he tells you in those ends of ginger, it is not working. Me, I'm waiting for O level. The secret you don't know is that there was a curriculum that had been designed in the science learning areas. I fought it. They designed another one very fast and called it competence-based and hid away the other documents, but I had all the documents from the inside. So, but then everyone else looked at me as if I'm confused, like I don't know what is going on, so I kept quiet. Because me, the secret I know is that it is not the way we teach, it is what we used to teach that was a problem. So now they made it worse. You don't have apparatus in the lab, now you are introducing projects. And then after introducing projects, you go to CAD, computer-aided learning. There is no electricity, there is no internet. And then you want to tell me that as a physicist, I will give students a chance, go and research and come and tell me about Newton's laws of motion, when I haven't even given them first. And then I start arguing with students. This one is saying, according to Newton, so I start listening. And then you don't tell me that you are a teacher is mature enough to be objective when I know that there are colleagues here who I should be taking immature, but they are not that. And then you tell me that these teachers will be able to award marks to this nice girl and give them actual marks. And this fake boy who is always lousy also give them objective marks. No. And there is no marking guide. Those days you could come and say, but sir, this number, this working is like this, why is it wrong? Now it is not there. There is no guide. The guy will listen to you and say you deserve 7. This one, 30. What will you do? It's like me marking your practicals. If I was to go by emotions or feelings, it would be worse. Because they are not the same results. The answer, even after calculating, is almost close. If we are calculating for G, we go from almost 8 up to 12. The actual answer is 9.8 meters per second square. I'm talking about acceleration with gravity. So you run away from a curriculum because it was not practical, and not because it was not practical that there were no practicals. It's because we were fake. We couldn't get the parameters. Now you move to projects with the poor parents who can't. How would you tell me to pay 1.5 to go to Dubai? 1.5 or 3 million to go, that you are making a trip to Dubai. The trips I saw, I think Namubongo, they shared the data of Namubongo with 1.5, 2.5, that because you want to take students and show them the Muhavola mountain and say that's how mountains or volcanic mountains form. And fees for another child is the one you want just to be spending. I wish you good luck in that curriculum. There will be just laughing. I've never been a sadist, but on this one I'll be a sadist. Because when I was trying to add my points, people started saying, there is one guy who I think is concerned with the consultants. When I was starting to fight, he said, but you can't just sit there and when things are almost getting out, you start fighting them. Where were you? So I kept quiet. That one I succeeded. It was supposed to be called learning area. So it was a science learning area, physics, physics, chemistry, biology were crowded together. So thermodynamics in physics would be combined with the endothermic, though that thermodynamics in equations of chemistry, then combined with the cell that metabolism of the cells and whatever of biology. Then you could call it a strand. That's how the curriculum had been written. And what annoyed me was that it had been initiated by an Irish guy, checked by an Irish guy, approved by an Irish guy, and people in NCDC here were proud, they were bragging that we are trying to decolonize the curriculum. Decolonize from where? An electron is an electron, whether I go to China or where. How are you going to call it? Akatambla? We have a special electron in Africa. So what they are trying to do, their children are being taken to China, their children are going to US, your children are making cakes. And everyone is children now can do something, they can make cakes, even fools in town make cakes. And you are telling me that my child now should be making cakes. That now they can have something to do when they finish. I want my child also to do robotics and do coding. Then the others put on boots and now they can look after the banana plantation. My mother never went to school. She fed us on her home. I'm quiet, but I'm like a landmine. You know landmine? When you step on it and when it creaks, you just look around and tell your friends bye-bye. Meet in heaven. Because there's nothing you can do. These things of films where someone goes down and clicks and or maybe they bring something heavy, and that is nonsense. The moment you step on a landmine, just tell guys bye. Or if you want to die nicely, you shoot yourself. Otherwise, they will not do anything. You just tell them, please go on, me, I'm going. So that's why I'm wondering whether it is my problem or whatever, that I look at things differently, others look at them differently. At the end of the day, they come back together. They come back to the same point. This curriculum will not work. Schools cannot manage project materials. Then you cannot produce a child who is knowledgeable. They will be just argumentative. This project thing, you tell them, you go and research, come and present. They want to make sure that they have now skills of making sure that what they have brought is correct, is important. That's physics, mathematics, chemistry. You argue with the students, where will they verify that this is right or not? Is it Senga? How are you? I'm good. Where did you sleep? You are still sleeping.
I'm leaving from Barara, so I'm tired.
You want to go back? We are welcome. When you had gone for a bazaar?
No.
Because I'm wondering why will you be in Barara on a Sunday?
Business.
Business. So, and I was asking before you came that, do you have any complaint about electronics? Semester system means that I never met you before. It's like I'm new, but I would love to know whether you had any problem.
Yes.
Where?
In electricity and magnetism.
Indeed, you are still in the vehicle. You are still there. I'm sure I said that you know.
The other one.
You had the problem with electricity and magnetism? No, not content about maths.
Yes, yes.
Oh, they are not there, they are in or what?
They are
more. Oh, they are more.
They are
You just saw them on Christian or you had seen them before?
I had seen them before. I came to your office. You told me you're going to change. You need to change.
Don't I choose?
It is on record.
That's why I'm saying I don't choose because I'm sure the few times you came, you are record. So, anyway, and that I was going to change that it was what? That it was, anyway, since it is about electricity, you can tell, but I don't think that I had any business with the electricity and magnetism. Max, that's a closed chapter. I'm talking about electronics.
So you can't change anything now.
No, but change how I put in, that it was like a 50, I put an 8.
You'll explain it, sir.
I explained.
I will explain.
Okay, but you have never talked about it.
We talked about it.
No. I've never talked about your marks.
For good.
I don't forget. I want you to put it on record now that I've never talked with you about marks. We've ever talked about other things, but not marks of electricity and magnetism. True or false?
I will remind you.
Huh?
I will remind you.
Anyhow, so these are the meeting times, and this is the CAS code. I don't think there is any group which those days I used to. If you look at the outline on online, it used to be 2105, then 3105 for different groups, but now we are having the same stuff. So I'll be teaching this book from cover to cover. It's a book by late Professor Banda. My notes are this exactly. These notes are on where, like the way for electronics and no, for electricity and magnetism. Electronics maybe I should also write all of them afresh. Then we shall be using this book. It is this is a crafted cover, but the actual cover is black with the curl of with the symbols of the curl of B and the curl of E. I think this is the book, Introduction to Electrodynamics by Griffith. I wrote to David Griffith to show him that I have videos, and then he said, I didn't know that something can come from Africa, so I never wrote to him again. I think I told you the story. I felt bad about the way he was blind in one sense, I mean in one way or another. So on the onset, we shall start on a course outline, but before the course outline, we got a course description here which will be found on Mwere. On Mwere, there is a syllabus, and then there is a detailed syllabus, just like it was for electricity and magnetism. The detailed syllabus is the I don't know whether it is detailed or which one did I use? Interactive or something like either interactive or could be interactive or detailed. One of these two words. Interactive in a sense that most of the keywords I made sure that I hyperlinked them to take you to Wikipedia. So that you can, if I say Maxwell, then I make you go to Maxwell and know more about Maxwell. Gone are the days. For us, the man would come with his small papers, you know, like a handout. He puts the course outline from there. We start from there, no textbook, nothing. So whatever he has given is what we will read. You got the textbook, also textbooks I struggle. Now I give you the videos, I give you links to other places. I like a generation. So the course description is that this course covers electrostatic fields, both in space and in matter. So we shall be able to understand how Wi-Fi works, and of course how the wire, how Ethernet works. Ethernet is this cable which you plug in your PC. And then for Wi-Fi, now I no longer have to brag about my internet. There is internet everywhere, either Eurodome, Edurome, Makea, whatever. And so we will be able to understand how these electromagnetic waves eventually are harnessed within the how we get to Wi-Fi. The SpaceX has Starlink, and Starlink is almost accessible all over the world. Much as Elon is, you know, launching satellites after satellite, and probably soon we will be junking up the space, having a lot of junk stuff. But who cares? Everyone thinks it is up there, no problem will happen. But I'm sure, because he's been launching 20 satellites almost every other couple of months, and I don't know how they'll be constructed. The constellation up there will not be good. But the beautifulness about the Starlink is that you can access it anywhere in the world. I tried to book the whatever, but I mean, we may never get the chance to access it because of our people. Dominance of our government. But I think Kenya, and maybe I should go to Kenya, then get the equipment, and then cross here, because it's satellite based, so it shouldn't be a problem. So that's what it means by, and when we talk of the, in the matter is that you know that you get do you know what this is? These are called banana cables. And then I remember making a joke, and so I used to say female and male. This is a male banana cable, this is a female banana cable. And I don't know whether that's why they are called. Apologies, that's how. That's how they are. But we shall understand why they are made like this. That you got these two cylindrical. Remember the cylindrical capacitor with an electric in the middle. And then you have the inside. You have the inside cylinder, outside cylinder, then the electric in the middle. So we shall be able to understand if you had all this matter being the wire transferring the electromagnetic waves, why do we reach here and try to make sure that we curl them and be able to be accessible here? So this curl here, these curls here, we shall be able to understand. So when we talk of matter, this is how how we can transfer electromagnetic waves in the matter. If I have a deck here or a DVD player, then I'll be able to transfer in the matter and take my waves to the screen, and then be able to watch the movie, listen to audio, etc. On the other hand, I can be on my laptop and then I cast to the device. I cast my laptop screen to the smart TV and start enjoying the movie, wireless, through space. As long as my TV and my computer or my other device, whether phone, smart TV on phone, as long as they are sharing the same Wi-Fi gadget. And then we shall look at including solutions of Laplace's equation in different coordinate systems. That is rectangular coordinate system, then cylindrical coordinate system, and the spherical coordinate system. Then there is magnetostatic phenomena. So when we are looking at the magneto meaning that we are looking at the magnetic fields, and then static. So if you looking at static field lines, if you got a magnet and you get two magnets together, or even one magnet having the North Pole and South Pole interacting. So this is the North Pole, South Pole, and you are having these field lines, originating from the north and heading to the south, and the magnet is not moving, nothing is moving around, so we have stationary field lines. And that one is, that's why it's magnetostatics. If you got stationary charges, then you got electrostatics. So the equivalent of electrostatics is magnetostatics. And so then we look at the magnetostatic phenomena, electromagnetic induction. I didn't come with a coil, but you remember the coil which we used to look at the Faraday and Lenz's law. And then the course actually starts from Maxwell's equations and propagation of plain electromagnetic waves in non-conducting media. And this course prepares you for graduate studies in electromagnetism. But I can say that this course prepares you to understand telecommunication engineering if you wanted to go out and change like Kassad, and they want to go and do a master's in telecommunication engineering, or you can do a diploma or a certificate or something just to make sure that you align yourself. So it's last year when I was having a party for students that I got to know that my talking sometimes pisses off some people, and I didn't know. Me, I don't know how to sweet talk you because I'm not your father. So when I came to class and told the students, BSc is a chance for you to repeat S6. Some people got annoyed. I think one boy even one of your friends went to do electrical down there because he felt, he was in the year which he were following. I mean, they go to tell me later, I'm not your father, that I come here and say, no, the truth is that you couldn't make it. You've come, it is graded as the lowest course, then also get your first class, go for a master's scholarship, do your PhD, then call yourself a scientist. Simple as that. So how should I switch talk you when I'm not your father? So one other student who actually was friendly to me, and when I asked them, normally when this course is done and I've made a party, I asked them, I normally ask students, tell me what you don't like about me. So he said that time when you talked to us, it felt like we are doing the course which is not important. But I think he will be getting a first class at the end of the day. Why should I switch talk with you? I'm not your father. I tell you what it is. It is a second chance. That's why I'm against people in Chitende, people in Mengo, giving a student who has been paying almost 10 million a year, you are giving him a course of 2 million a year. And you expect them to love you and chop Maxwell's equations. And then every one of their friends is telling them, what course are you doing? Flat course. What will you do? I don't know. But is it true that you don't know what you do? Kasada. You finish now with your first class, you do a PGD, you are at the top of the teaching nature. You do a computer science master's, you become a computer scientist. No one will ask you what you did at undergraduate. Even education, there are many people who have chosen to do education, then go for masters in computer science, for engineering, whatever. Then they have changed. Others have gone to renewable energy and have changed their direction completely. Me, I just want to teach. I just love teaching. If I wanted to be in politics, maybe I could be an RDC. Can't I be a good RDC? Can't I really go convince people and explain stuff on TV? Policies, what convince people to like himself and I like? What do you doubt? That I can't convince or convince them to like you? Yeah, if all fails, I'll be a pastor. I think I can.
By calling or by calling or
There?
by calling or by passion.
No, by calling. You know, when you accept the Holy Spirit, everything is possible. When you believe, when you accept Jesus into your heart, you are touched by the Holy Spirit. Amen. And all okay, so now let's start the course a bit. And before we start the course, the objectives of this course are that at the end of this course, you know, this is why I start from day one, so that we set the pace. And then these other coming days, we really do the core of the stuff. But today, I mean, this first week, when we are done with the course outline, rules of engagement, lab stuff that we shall do, then but these things of 2 weeks, that for us 2 weeks, we take 2 weeks. Who said we have to take 2 weeks without going to class? But you know, it is our culture. It has never been my culture. And for me, if I had authority, I would make sure that whoever was not there the first day will never get beyond the 60. If I had authority. But so the objectives are that you should be able, at the end of the course, be able to apply the expression for electrostatic energy density in both free space and electrics. Yeah, this objective is funny. No problem, don't know why. You should be able to explain polarization of matter and calculate the forces on the electrics in the electric field. Solve Poisson and Laplace's equation for simple electrostatic problems. So you remember that guy who, after Gauss had done all this stuff and explained that when you try to diverge electric field lines, here we are going to, in this course, we shall be trying to divide electric field lines to make sure that we can do some communication, so that they can be felt somewhere. So if you can divide them, so remember when we are doing this, Gauss said that you can only do this with the comfort of having that much charge that you'll be using. And then you must be very cautious about the permittivity of where you are doing this. So whether if you're doing it in free space, of course that will be the cell map, the 8.85 and then 12 volts per meter, or if it is any material that you are using, whether a piece of wire like I've been having or another cable, whatever way you are using it. So this is Gauss's law, and we normally call this one in differential form because of this baby here, which is the Kali by Kali X plus Kali by Kali Y plus Kali by Kali Z. This should be K. I'm sure you no longer argue with me about Z because you had the Gen Z of Kenya. You didn't hear them as Gen Z. So this is why we call it the differential form, and this is because of these partial derivatives which are called Kali by Kali. When we talk of integral form, then you should be having an integral somewhere there. And this is why I have a problem with students when I'm teaching electromagnetism. You say, state the differential form. Somebody integrates comfortably, puts an integral and writes, and you say, state differential form. Sometimes I feel like boxing somebody, but I normally mark when I'm away from people. So then here is where we say that, but this, according to the scalar potential theory, this is minus grad V, where V is the scalar potential. In mechanics, this will be finding it as grad minus grad phi. And then when we substitute it in, end up with grad squared V is equal to minus rho over epsilon. And this is the one which, after substituting, this guy also brags and says, this is my equation. Calls it Poisson equation. Then Laplace comes around and says, but you know guys, in places where we don't have any charge, then grad squared B equals 2, and he says this is our equation. I really hated this guy for this, but because of what we shall be using his equation for, I gave him a second chance. Like I pardoned him. Because we shall be using Laplace's equation to solve small, simple potential problems. If we have a system of, let's say, 2 electrodes, and we would want to know the potential in between them. Like you have 2 electrodes, an electrode here, an electrode here, and they are running up to whatever, infinity, but you would want to know what would be the potential in between them. You can use these and then solve the potential problems, both in cylindrical, in a rectangular. What is the other name of rectangular? Cardinals? Cartesian. So in rectangular, Cartesian, then spherical, and cylindrical. So the solving, I just reminded you of the Gauss, then Poisson, and Laplace, to make sure that you understand when we say that by the end of this you should be able to solve Poisson and Laplace's equations for simple electrostatic problems. Then you should be able to describe the behavior of conductors in static electric fields. So what are the properties of the conductors? The conductor, if you have the conductor, eventually when nothing is going on, it has the same positive and negative charges inside it. So that means it is neutral. If there is any charge that would reside anywhere, it would be on the surface of this conductor. And if any charge of this charge produces an electric field, that field will be perpendicular to the surface of the conductor. And of course, when you have the potential inside this conductor also will be the same. And if the potential is the same, charge was neutral, potential is the same, so you will be having the actual potential will be constant, not the same. Then be able to derive, use the simple models to explain magnetization of matter, and then derive and apply boundary conditions in electromagnetic field waves, mean vectors. When we talk of field vectors, E, H, B, and which other letter? B equals to mu H. What is equal to epsilon E? So the other one is B. These are called field vectors. So this is the electric displacement vector. This is the magnetic flux density, electric field intensity, magnetic field intensity. And then you should be able to state Maxwell's equations and use them to derive the wave equations. And then explain the effect of plane boundary between two different media on electromagnetic field vectors. And then we have the course outline, which I'm not delving into. But I just want to make sure that we do something small here, and we start on the outline right when we finish it today, because I always want to use the outline to finish the course. Like go through the course, and so I don't know. If I start on it now, I will not finish it. And then when the other feathers come, then we start afresh. So I want to use these to make sure that we do some bit of stuff. So we have Maxwell's equations, which will be the most, okay, not the most. This is the course. But we shall do a lot of stuff before we reach there. I'm just making sure that we spend this little time left and get something before, better than the other guys who are not here today, because I want to repeat it until when we reach Maxwell's. So Maxwell tried to look at the four equations and group them together. And these equations mostly are these equations here plus some other bits. So for example, we have an equation, this other one, this one here. If I take this one here, it means it will be divergence of D equals to rho. And so we have that the divergence of D equals to rho. This is for D. What would be divergence of D? When you diverge electric field lines, you depend on the amount of charge you got and the permittivity in which you are chasing. But I put this back here to make sure that we get electric displacement better. So what you do for electric fields, we do it for magnetic field lines. So what if I have a magnet? I don't know, I wrote it here. But if I got a magnet, or if I got a wire carrying a current I, and it creates the field lines around it, if I diverge these electric field lines, if I now try to diverge this electric field line, what do I remain with? So, if I get these field lines and I start diverging, what do I get?
You create some region there. A neutral region which has zero magnetic force.
Get zero. So you get zero. So this is about diverging. Diverging electric field lines and diverging magnetic field lines. Hello? You want somebody? Where are you from? Yeah, he was there. That's why I phoned him and I came here. I also told you to come here also. So we are done with the diverging of the electric field lines. And the whole struggle, the struggle we go through, the struggle that the reason they put that mast up there is because they are trying to make sure that they can diverge the electric field lines as far as possible. The mast is just near the dust bin. You know, African empty heads, you put a mast on a place, then below it you put a dust bin, garbage collection bin, and then hostel buses are parking there. Instead of making it a nice looking place, put seats there, so that when students are waiting for hostel buses, they can be accessing the nice signal. So how about if we call when we call the electric field lines, we have the electric field lines going like this, then we try to call them. What do we get? You have the field lines, and then you call them. You can call them and maintain something happening as long as you can continue producing them. So how do we produce the electricity? How do we produce electricity? We move the character within a magnetic. In other words, we change. But because we are carrying, this will affect our change. We are changing, yes, we are doing the change, but we are also carrying. So it means whatever we are producing, we are reducing it. Hence this negative here. The fourth equation is that when you curl the edge, the magnetic fields, if you get the magnetic fields, these ones here, and you spin them up, these ones here, you curl them, you squeeze them up. When you squeeze them up, then you get an issue. You get the current density. It depends on how much your current here going through that area in which you are carrying. That area that you have in which you are trying to concentrate them by carrying them. Carrying means you are trying to bend them into that area. So it will be the current there, this current per unit area, this area here of this But remember when we were deriving the Ampere's Sakiro law? We did RL and then we have to consider this. So this area here, then with this current here, gives us the current density. And then we try to add something, some correction in relation to the electric displacement vector. So we have the carry d by, and this is called, this whole thing is Ampere's law, but with Maxwell's correction. You take care of the electric displacement vector. So this is Maxwell's correction. So these are the four Maxwell's equations. And Maxwell sat down and tried to work around. I just want to check whether they are the ones. I might be giving you chemical. Impossible.
They are the ones.
They are the ones. How do you know?
I'm doing them.
You have seen them before. When you are doing research. Okay, so now we wanna try to make sure that now that we know the relationship between the electric and the magnetic field, and then we know how they are affected by the divergence, when we try to diverge them, and then also when we try to curl them. If you are trying to move your even when you're having an element, an alien, at the end of the day, where you are plugging in your TV, it is curled. I mean, it is, the stopper is like this. It is not like, otherwise you would just be having two ports where you can put one wire and another wire. But we curl them like this. So this is the curl. So we now know how the electric and magnetic field vectors, how they are affected by diverging them and how they are affected by curling. So how can we trace that to make sure that we understand how propagation takes place? So I'm going now to show you how I always want the latecomers miss, but not directly. So when I meet them, when we meet them next time, we meet tomorrow. It's like we are meeting, so they don't know we did stuff. Because there should be a consequence for any action somebody does. So it means there's not much we can do with these two. One says you diverge magnetic field lines, whether they were coming from the north going to the south and we diverge them, it's like we have killed everywhere. Otherwise we would get only the force, the magnetic force would be experienced in that region where we have the field. We have curled it, diverged it, so zero. To diverge an electric field, we have to be concerned about how much charge we got. So it means we have to have a constant supply of charge, and also we must make sure that the place is permitted with the permittivity of free space. So the one which looks like, something is hidden in there are these two. So then let's see. If we went ahead and even curled this one, what happens? So if we take the curl of equation 3, then we would have, sorry, this stroke is really poor. Either quality of the stroke or quality of the form. So if we curl the curl of E, this would be the same mathematics. What is the curl of the vector A? So during this course, I will not bother you. I will make sure that I give you answers in exam. These answers are these identities. So I don't expect you to cram. One of the pages will be having these identities, and the identity that we are having here is that when we get the curl of the vector, that should be equal to, so the curl using the identity curl of the vector A being the same as grad divergence of the vector A. No. Yes. Then minus grad squared so I use the same logic. This would imply that this other equation here would give me the grad divergence of E minus grad squared E equaling to, this would be, this okay. I just take it as it is for now. And then, so here, the divergence of E is minus rho of epsilon. So this is rho of epsilon minus grad squared E, which is equal to minus curl of Khalil E by Khalil T, and this should be mu. No, not E, this is H. B is equal to mu H, and D equals to epsilon E. Since D equals to mu H. So this would imply that this is a constant. This is a constant. What would be differentiating a constant? So this is approximately equal to 0 because rho of epsilon equals to a constant. So then we would have, this would imply that we have 0, so 0 minus that, so we have minus grad squared E equaling to, then now this is the same as minus mu Khalil by Khalil T into the curl of H. But the curl of H is J plus Khalil by Khalil. So this is J, the curl of H is J plus Khalil by J. What is J equal to? From the microscopic form of Ohm's law. And D equals to epsilon. So that means that we will have that minus grad squared E, chalk is really is equal to not supplied in boxes which look like they are normal. So this is the mu minus mu. We have said this is sigma E, so minus mu sigma Khalil E by Khalil T, then minus, these are squared, so this mu combines with the epsilon here, and then squared E Khalil T squared. We can arrange this in a more beautiful way. And when we arrange it in a more beautiful way, we put this one on the other side and equate to 0. So Therefore, grad squared E minus, when we are trying to arrange equations, differential equations, we follow the order, their order. Order of what? How do they call it? These powers here. Don't you do mathematics? No like terms, I'm talking about the order. This is Kali by Kali T, this is Kali squared by Kali. So when I'm writing it, I must make sure that, because this is the second differential in X, or Y, or Z, whichever it is, and this is a rate in time, I put them in their order. How do they call that in mathematics? So this would be mu epsilon Kali squared E, Kali T squared, then minus mu sigma Kali by Kali T, and this should equal to, this equation is already a wave equation, if you look at it closely, but it will even be more beautiful soon. So I will put here 5 as grad squared E minus mu epsilon Kali squared E by Kali T squared, then minus mu sigma Kali by Kali T equals to 0. So this is what results when we do when we try to squeeze this other equation again. How about if we do it here? So if we do for equation 4, that means we have H here, so you will do this. This is mathematics. You can follow this and do it. And we shall do this in the future. So I just want to make sure that we shall be doing this, but because this is our first day, I wanted to make sure that you get a notch. Because if we reached that end, some of you will be already annoyed by the marks from tests. But now you are happy, you are seeing things for the first time, so you are excited too. So but you can follow the identity is on the, even on Mwede. I follow that I haven't opened up the other weeks. So I call now the equation 4. So that means I take the curl of H being the same as the curl of J plus Kali T by Kali T. We've already said that this one becomes grad squared E, grad divergence of, now this is H minus grad squared H being the same as the curl of J. How do we call this in mathematics? Plus the curl of the Kali D by Kali T, but J equals to sigma E, the microscopic form of Ohm's law, and D is equal to sigma A from the polarization of matter. And so this would imply that the other one became 0 because we are differentiating a constant. This becomes 0 because that's what the law says. So from equation 2, this one equals to, from equation 2, that divergence of B equals to 0, B is equal to mu H, we divide by both sides by mu, we get 0, so mu divergence. So when you diverge magnetic field intensity, you get 0, because diverging the magnetic field lines, you neutralize, you make everything disappear. So then we got the, so minus grad squared h is equal to, this one is sigma, the curl of E, plus the other one is epsilon, the curl of Kali E by Kali T. And so this would be the same as the Kali, we can put the Kali on the outside. And so, but when we try to curl the electric field lines, then we have to be aware of how we are producing them. And we produce electric field lines, the electricity, by changing the magnetic field. So when we have varying magnetic field lines, that's when we are able to produce electric field lines. And once, how we do that is because we are having this minus here. That minus is to show you that you are doing something but also trying to reduce it at the same time. You are trying to do it to reduce it at the same time. Remember when we were looking at the equation of continuity, when we are having our charge posted within a volume bounded by a surface. And then you're having the charge that is in here escaping at the rate. That escaping through this one ended up being the current density, because you got a current constituted by the charges which are escaping, and then because that current is going through the surface, gives you the current density. And then when we eventually had to say that the divergence of this current density would also be related to the amount of charge you are losing that is escaping this surface. And that is the equation of continuity came up as the divergence of J being the same as minus Kali rho by Kali T. But we wrote it nicely as divergence of J being this plus Kali rho by Kali T equal to. But the actual idea is this, that the amount of charges escaping are constituting a current. That current is going through the surface area, constituting now a current density. And that current density, you can have as much going out as how much you will be losing from this escaping the surface. As most of you want to program it. Divergence of J equals minus Kali rho by Kali. You don't even know why it is happening. The reason is that you are having charge escaping, that charge is causing the current density. And that current density, as it is diverging, is being related to the charge that is escaping. The minus is to show you the escape. And then the Kali rho by Kali T, that rate is the change. You are having that change is because it's going away, the minus shows you that. So we get back, we put back this, and so that this would be the same as sigma mu. So this is minus sigma mu, and then Kali, the curl of H. Aren't we going to get back to but this would be the Kali H by Kali T, and then minus, the other one will be mu epsilon Kali squared H by Kali T squared. And this is equal to minus grad squared H. Therefore, when rearranging to make it look nicer, we have the grad squared H, and then minus, we go to the orders. I don't remember the order of what. Is it what order? My mathematics. The mathematical methods confusing. So mu epsilon Kali squared H by Kali T squared minus mu sigma Kali H by, and this should equal to, this is our equation 6. that they are second order differential equations, and which we look as wave equations. Now, if we were to be in free space, if we are in free space, so in free space, when we are in free space, epsilon equals epsilon, mu equals to sigma equals to
0.
good. We are done. Mu naught, epsilon naught, 0. So equations 5 and 6 become equation 7 and 8. So we got a grad square E. This other part here disappears. So we get minus mu epsilon naught, mu naught, carry squared E by carry T squared equals 2. And this is equation. Then equation 8 becomes grad squared H minus mu naught epsilon naught carry squared H by carry T squared equals 2. 0. Does something ring in your mind? So this is compared to the classical equation, wave equation, which is grad squared psi minus 1 over c squared, or we use v squared, nu squared. Grad squared psi and t squared equals to 0. If we are in free space, then but before we do all that stuff, let's be nice like this. So once we do this here, we can compare. So comparing these equations with this classical equation, then we get that 1 over v squared equals to mu naught epsilon, mu naught epsilon naught. So that means v would be equal to 1 over root epsilon naught mu. So can you help me, those of you who have colors, or whatever you're going to use for that, can you help me to see whether 1 over the square root of 8.85 times 10 to the power negative 12 times 4 pi times 10 to the power negative 7, what is going to give us? Second, I'll also show you with the phone. So if you want to get a scientific calc, you just turn your phone like this. Once you have calculated, you put it in landscape, everything comes up. When it is in portrait, it is a small thing, and you put it in the landscape, everything comes up. You should be able to do amazing stuff. You don't know the permittivity of free space.
I know.
8.85 to 10 to the power negative 12 parts per meter. This is the one that didn't come out well because of this fake expired. Does chalk have expired date?
It's 3 exponents.
3 exponent 8. How do I write that? 3 exponent 8. That's what you say.
3 times 10 to the power 8.
So this means that B equals to 3 times 10 to the power 8 meters per. It means that when you do curl these vectors, field vectors, electric and magnetic fields, you are able to actually make them move at the speed of, and that means this was the time when Marconi tried out the transcontinental communication with the radio. And we are now able to watch everything, the premiership, whatever. And when you are now chatting with somebody in the US on WhatsApp, you see the blue ticks coming up just the moment you have just said send. And then the alarm rings. So after this discovery that the magnetic and electric fields can move at the speed of light, this was the genesis of communication. And that's why I was saying that I'll introduce you to the communication. And once we also go to the part of what the Newman theory is that if you have a coil here and another coil here, and you are able to vary the current in this coil so that it can produce the field that can enangle or can interact with this other coil here, then you would have made these two coils to communicate. And that's how mobile phone works. When I ring you, I have created a field in my phone, then it should be able to come and induce a field in yours, and then your phone starts ringing. But we need to enhance that signal. That's why we need cellular masks. And that's why it is called a cellular phone. Because each mask, each tower, if I can use the language, each tower has a booster there to make sure that when I create a field here, it enhances it to go to other phones. So you need many, when you see masts being erected everywhere, it's because you are trying to make sure that you enhance the Newman's formula, to make sure that the field that I create in my phone is enhanced to go to the other phone and then create. And then in this formula, it wouldn't matter whether you're the one who called or me who. What matters is the geometry of the coils in my phone and the coil. Well, that's the basis, but things turn out to be looking different. I mean, when one would wonder, when is the coil in this phone? Because of the advancement of stuff. So this is the beauty, this one here is the beauty of the course. Whatever we shall be doing is what the Baganda call Kwei Sako. Yes, we shall be doing that to understand what we shall be using here. We shall be doing electrostatics to know how these field lines are caused, how they are moved, how they interact with the meridians. Then we try to solve the potential problems to say if we are having a transmission line, how will this cable affect our E and M. Then we shall try to understand the conductors, because we're going to transfer our electric and magnetic field lines in cables like this. This is a banana cable, which we no longer use these days, because I just go to the internet, I download my movie, put it on a flash, stick it into my LED TV, my flat TV, and I start playing. And if I have Benos, I just put my smart TV, and directly from Google, from YouTube, I start enjoying the movie. So things are slowly, like when I was looking at the communication system, I was wondering whether I continue talking about the AM and FM modulation, AM modulation. We are going away from that. We are now streaming online. So Things are changing, but you need to know the basics. Then you can be innovative. Innovation is from you. I am not charged or obliged to teach you how to be innovative. I'm supposed to give you the basic knowledge. It is you to see that knowledge as if it is applicable somewhere. If you can't, don't blame me. I was not taught how to make people be innovative, and it is not my role either. I will show you how in the future. Any questions? So I just wanted you to have a difference from the other guys who were not here today. And so tomorrow we shall write down the, okay, I will try to come with more stuff to demonstrate mainly about the planets and the like. And then we start on the, we finish the course tomorrow. And then during the semester we try to just, work around seeing whether what we finished is finishing. Because that's how I take the class out. Tell your friends who were not here today that for me, I don't care whether you are here or not. Me, I was going to teach myself. Whether you say it rains like cats and dogs, I told you, did I do moon viewing for you? Yeah, so I told you how rain happens. Today is first quarter, it rains. So you should know whether it has been shining or whatever. So you can't say it rained. You knew it was moon or rain. So, it was nice meeting you again. Hope to have a good ride in this course. And everything is on way, including lectures of videos of my previous lectures. Just like it was for the Electromagnetism.